Thank you. All right. So so my first advice, guys, is try to sketch, the region. That's really important, right? So because so you can figure out the bounds for the integral. So like here, let's say this is 0, this is 1, 2, etc. This is 1 here. For example, x fourth. So you graph, let's say x to the power 4, I guess it would be something like this here. All right, this is my x power 4. All right, and then x to the power 5. So x power 5 would be something like, let's see, x power 5 should be, something which looks like this here. This is x fifth, right? And becomes negative here. Should be negative here. All right. Anyway, so once you sketch the graphs, then you can see, well, what will be the region which is bounded by the graph. So like here in this case, we would have, so here these two functions, right? They intersect at the point 1, 1, right? And the point 0, 0, for example, right? So if you have 2 graphs or 3 graphs or wherever, right? So they're gonna intersect at I don't know how many points, but so like in this example, they're gonna intersect these 2 points. So so then the region bounded by the graphs of these 2 functions would be this region here, this one here, right? So I mean, either in the problem 2 or 3 in the homework, first you have to sketch the graphs, and you have to find exactly what the region bounded by the graphs, right? So in this case, we have this region. So then my advice would be just to say, well, so I have this region, I have, I have this point 1, 1, right? And I have this point 0, 0. And here's my region, right? My region D. Now, guys, so you can either start with the x or y. So let's say you're gonna fix y first, okay? So you're gonna try to find the constant, the bounds for y, okay? So for example, if you start with y, then you can say, well, my y coordinate, so I have to find the bounds for y. So the bounds here first, they should be a constant, right? So here I'm gonna start with a constant. And then for my x, okay, and then for my x, I mean, you can start either with the y or the x. It's up to you, right? So you can here it should be functions. Okay, and as I said, you can interchange x and y. You can instead of y here, you can say, well, I can start with x, find the constant, the bounds for x, and then I can, find the bounds which are functions, for y. So, for example, here x. Well, I have these 2 points, right? So, what's the x coordinate of this point here? X coordinate is just 0. So here, the x coordinate is just 0. So this is actually x equal to 0. So x equal to 0 would be this line here, right? Here in the top, in this point here, x is equal to 1, right? So if you pick the x coordinate is equal to 1, right? So if you take the equation x equal to 1, that would be this line here. Okay, so my x would be, for example, here would be between 0 and 1. Okay, so that would be the constant bounds for x. Now, if you want to try to find the bounds for y, they should be functions. Okay, they could be also constant, but they're supposed to be functions, right? So the functions here, your y, well, the left side here, this side here of the region, this one here, there should be a graph of some function, right? And this function is in this case would be this one, which is y equals to x to the power 4, right? So this is like y equals to x to the power 4. And the other side here, this side here, it's given by y equal to x to the power 5. Okay, so then y would be between x power 4 and x power 5. Okay. And so when you integrate, so then the area of this region D, of course, would be just, so the area of D would be just a double integral of the function 1. So here my x is with respect to the bounds for x are constant. Okay, so and the bounds for y is our function. So we start by integrating with respect to y. So here's dy and then dx. So your x would be between 0 and 1 and y between x fourth and x fifth. Okay, and then of course, and then you integrate. You can also, you can interchange, as I said, x and y. So if you, like in this case, if you interchange x and y, or you change, if you want to change the order of integration, interchange x and y. Okay. Well, you can say, well, my y between, well, here the y coordinate is 0, so y is equal to 0. And here the y coordinate is 1, so y is 1. So then y would be between 0 and 1. Okay. And then x would be between, the graph of these, these two functions here. This one here and this one here, right? Well, here it's y equals to x to the power 4. Of course, you have to solve for x. Then x is, because it's even power, right? So x is supposed to be plus or minus the fourth root of y. But here we are in the first quadrant, so x is, it's positive, and y is positive too. So it's just, plus fourth root of y. And here x power 5 is all for x, then x would be equal to the fifth, y is positive, x is positive, so x is fifth root of y. All right. Anyway, so the idea is, all I'm saying, guys, is just you have to sketch the region, and then you can find the bounds. Okay. I don't know if this helps. I mean, this is well, they're very similar to the problem 3 and 2 in the homework. And again, it's just the same. It's the same idea. Okay, I hope this would help. All right. Okay. Perfect. And then you said, guys, you had trouble with 1.3, right? There's this integral. I mean, yeah, I'm kind of, this is kind of very special. I don't know. It's why they have all these kind of hard, kind of not obvious integrals in the textbook. But so this is, let's say, exercise. So like you have to integrate. Well, I think so. This is, let's say, similar to the problem 1.3, right? I mean, in problem 1.3, first you have to integrate with respect to x, so it's just constant, so it will be just 2x. But then you substitute x with this square root of 1 minus y squared. So basically, you have to integrate square root of 1 minus y squared, right? That's the problem, guys, right? For you, is how to integrate the square root of 1 minus y squared, I guess, right? But anyway, I mean, we had the same kind of same problem. I mean, not problem, but I mean, same problem like in the last week. the square root of 1 plus y square or something. But anyway, so the idea is if you have, for example, so if you have this square root of 1 minus y square, all right, so we have to do sort of, so in this case, 1 minus y square, you know, it reminds you like kind of trig identities, like you have x squared plus y squared equals to 1. So this is like cosine squared plus sine squared equals to 1. This is, let's say, dy, right? So the idea, guys, would be, for example, here, as I said, it looks like some trig here. We have some trig identity here. So probably the right thing to do here is just to say, this is, you know, because, you know, cosine square plus sine square theta is equal to 1. So then you say, well, let's say, for example, cosine square is 1 minus sine square, right? So then cosine would be, for example, plus or minus the square root of 1 minus sine square, right? So in this trig here, you see there's this square root of 1 minus sine square. So the idea here, this 1 minus y square to the square root of 1 minus y square, the idea here would be probably to use some substitution with the trig functions. So probably you should substitute, let's say, cosine of theta equals to this square root of 1 minus y square. Okay. And then, so what would be, our integral here? Well, just to remind you, there's also trig identity sine of 2 theta. This would be also useful because this is actually 2 sine of theta cosine of theta, right? So that would be like 2 sine of theta cosine of theta. So 2 cosine of theta is this square root of 1 minus y squared, right? And then sine of theta would be, would be where your y, okay? Right, because here we are saying cosine of theta is the square root of 1 minus y squared. So y here, basically we are saying y is the sine of theta, right? Anyway, so when you integrate and use this substitution, so you'd have, you know, your integral. So the square root of 1 minus y squared dy. Of course, here y is positive, right? Everything is positive here. Positive was 0, of course. So it's just cosine of theta, right? This is the square root of 1 minus y squared is cosine of theta, right? So we're gonna have square cosine of theta. Now the question is, what will be dy? Well, y is the sine of theta, right? So derivative of sine is just cosine. So then dy dy would be cosine of theta, right? So it's cosine of theta d theta. Okay, so this dy is going to be cosine of theta d theta. Okay, so that would be cosine squared, and then use some trig identities here, you know, to integrate this cosine square. So this is equal cosine square theta d theta, right? And then, I mean, again, just I'm using trig identities here, right? So this cosine square of theta, you can use the fact that cosine square of theta is equal to, I guess, 1 plus cosine of 2 theta over 2 or something. I think that's the case. So this is 1 plus cosine of 2 theta over 2. the theta, right? And this is kind of easy to integrate, right? Because you know, this is just I mean, this is just the integral of 1/2 the theta plus the integral of cosine of 2 theta over 2 the theta, right? This is easy to integrate. And this one here, cosine of 2 theta, you can just use a substitution here, right? So this is here substitution. You can say, for example, you can say u is equal to 2 theta, right? And then it's the problem is solved, right? And then of course you replace everything in terms of y. Does this make sense to you guys? So that's the how. I mean, if you want to integrate this square root of 1 minus y squared dy. Okay, you have to use some trick or integration by parts, either way. So because as I said, when you see square root of 1 minus y squared, 1 minus y squared should remind you like kind of the trig identities, right? Like cosine squared plus sine squared equals to 1. So like cosine would be square root of 1 minus sine squared, right? And this is kind of, again, this is like similar. If you had the plus, I mean, if you had the plus, so I mean, last week we had this 1 plus y squared, you know, square root 1 plus y squared to the power half dy. So if you had the plus, well, this is kind of different from this one. Here it's minus 1 minus y squared, right? And as I said, 1 minus y squared would remind you of 1 minus sine squared or something, right? It will be, then you can just use this trig, right? Here it's a 1 plus. So it's not, well, in this case, you cannot really use the trig directly. So first, probably you should go with the integration by parts. You can integrate by parts. Okay, so how do we integrate by parts? I mean, this is like, here's 1 times this 1 plus y squared to the power half. So like, then like your, let's say your u prime would be equal to 1, and your v is equal to this 1 plus y squared to the power half, right? So then integration by parts, there will be u times v. So u prime is 1, so u would be y, right? U would be y. So that'll be y times this 1 plus y squared half to the power half, minus, and then you would need u, which is y, okay, times v prime. So that's the derivative. So v prime here would be like y times 2 times half, and then you subtract 1. So that's like 1 plus y squared to the negative half, right? Anyway, so then u, so this is uv, and this is u v prime. So that would be y squared 1 plus y squared to the power negative half. Okay. But anyway, guys, the thing is here, this, you see this 1 plus y squared to the power negative half? Like, it's like having 1 over square root of 1 plus y squared, right? So this should kind of remind you of, 1 over 1 plus x squared. So what would be the integral of, what will be the integral of 1 over 1 plus x squared dx? That's the arctan of x, right? Okay. So anyway, so this should I mean, this integral here, this part here should remind you of this identity, this integral of 1 over 1 plus x squared. But now, of course, we have this square root. But the idea here would be almost, you know, so your y. So here, the idea would be to use a substitution here. So then you'd have like, you'd use the y equals to tangent of theta, right? Because, you know, because of this integral here, right? This 1 over 1 plus x squared integral, it will be arctan of x. So if you have 1 over square root of 1 plus y squared, you should go with this substitution here, y equals to tan of theta, right? Because of this here, right? Anyway, so you can use this substitution with some integration by parts, and then you're gonna be done, okay? Anyway, so all I'm saying, guys, is that if you have this one of this like square root of 1 minus y squared or square root of 1 plus y squared or whatever, you should think of integration by parts and also of the trig. You try to use probably trig substitution here. Anyway, I mean, I hope this answers your question for the 1.3, right? Does this help with the 1.3? Well, at least for this square root of 1 minus y squared, right? That's how we integrate this square root of 1 minus y squared using this trig substitution. Anyway, so I mean, this should be like, I mean, all these integrals, the square root of 1 minus y squared or square root of 1 plus y squared, all these integrals, they should be studied in Calc 1, right? It's just some like very standard tricks. Anyway, Enrique, you said you had another trouble, or David, you said you had trouble with the problem with some integral in problem 4.
No, it was me.
No.
It was
No. Okay. Anyway, I hope guys this helped with the 1.3, right? This is how we integrate this 1 minus y squared to the power half. Anyway, okay. Is there any other question, guys?
Yeah, so it was me with a question for problem for number 3.
All right.
I'm having issues solving that.
4.3. Let's see. First, yeah. Well, number 4, the idea would be, of course, to change the order of integration, right? I mean, in the problem 4. So we have to change, of course, in all the in the 4 integrals in the problem 4. You have to change the order of integration. All right. So in number 3, well, so you know, like, so this is like number 3. So your x is between 0 and 3, right? And y is between 0 and 9 minus x squared. All right, so 0 and 3, 0 and 9 minus x squared. This looks like the first quadrant of your disk. I mean, if you graph, if you try to sketch this region here, that will be, so x is between 0, this is x, this is y, between 0 and 3, right? And sorry, y, no, it's not square root, it's y equals, sorry, it's not circle. I thought it was a square root of 9 minus x squared. So you have y so x is equal to 0. This is where x is equal to 0. So this is where x is equal to 3. Right? And then you have y equal to 0. So this is where y is equal to 0. And then you have y equals to 9 minus x squared. So this is a parabola, so we should y equals to 9 minus x squared. So for example, if x is 3, then y would be 0. So let me just graph this. So this is when x is 3, y is 0. Then you know, this parabola here, this is so you have so for example, x is equal to 0, y equal to 9. So it's going to be somewhere here in the top, wherever. Anyway, this parabola is going to open down, right? And it's going to be sort of, so this is your parabola here. So here's your parabola here. This should be all right. Anyway, so this is the point. This is 9, of course, right? So then your region would be this one here, right? This is the top here. This is 9. Y coordinate is equal to 9, right? So you change the order of integration first, guys, right? So if you start with y, so then the y coordinate would be, so then y coordinate would be between, here in the top, this is y equals to 9. And here in the bottom, this is y equals to 0. Okay, so y should be between 0 and 9. Right? And then what about x? Well, x would be between, you know, this line here. This is x equal to 0, and the graph of this function here. Right, so x is, let's say, between 0 and, so we have to solve for x. So, I mean, y is equal to 9 minus x squared. So, of course, x squared would be 9 minus y. Then x is, of course, because it's even power, just be careful. This should be plus or minus 9 minus y. But your x, in this region here, your x is positive, right? The x coordinate is positive. So I'm going to just take the plus. So it should be plus square root of 9 minus y squared. Okay. Does this make sense to you, Enrique? Did you get this, these bounds?
No, I didn't, but I understand now.
Yeah, so anyway, in all the problems, in the 4 integrals, in the problem 4, you have to change the order of integration. I mean, that's the goal of the exercise, of the problem, okay? Now, once you change the bounds of the integration, so let's see here, what's the integral? You have this x e to the power 3y over, I mean, I won't solve completely the problem, but I'm gonna just tell you like the big lines here. So this is no, so 9 minus y, sorry, so 9 minus y, and here is dy dx. Anyway, okay, so you change the order of integration, so now it's dx dy. So now it's dx dy. So y between 0 and 9, and x between 0 and this square root of 9. Sorry, it's not y squared. Why I put the y squared here? It's not y squared here. It's just y, right? It's 9 minus y, right? Anyway, so you integrate with respect to x, and that will be easy to integrate, right? Because, I mean, you only have x here, everything else is a constant. So you have just to integrate x, that will be x squared over 2, right? if you integrate this, it'll be x squared over 2 times the, the rest. And then you substitute x with the 0. Okay, that's cool. And then you substitute x with this square root, right, of square root of 9 minus y. But then because you have the square and you have the square root, so they would cancel out. So that would be just 9 minus y. And I guess that would make the computations, the integral, easy to compute, right? I guess, actually the 9 minus y would cancel out with the 9 minus y in the denominator, right? So I think we just end up with this to integrate the e to the power 3y, if I'm not mistaken. Does it make sense to you, Enrique, now? You
yeah,
see what I'm saying?
completely. Yeah.
Okay. All right. Any other questions, guys, about the homework? So yeah, this is actually a good thing, because just to remind you, so the homework is due this Thursday. Any other questions, guys? Let me see. Nope. Okay. Then all right. So now let's move to the material for today. So yeah, we finished the double integrals. So now we're gonna start the triple integrals. So I'm gonna just probably move the next page. All right. So yeah, so let's start this triple integrals over rectangles. All right, so for triple integrals, guys, so we're gonna have functions of 3 variables. So we're gonna have, let's say, f of x, y, z, a function of 3 variables, a continuous function. And then, so we're gonna start by integrating over, let's say, boxes. So I'm gonna consider the box, so that be the box. So remember, in double integrals, we started by integrating over rectangles, right? So if you want to extend this to the 3-dimensional space, so instead of rectangles, now we're gonna integrate over boxes. So the box B here, so B would be equal to, let's say, interval AB cross the interval CD cross the interval, let's say, RS. So the variable x, so x is in, belongs to the interval AB, y is in the interval CD, and z is in the interval RS. Okay. If you wanna sketch this box here, so we're gonna have like, so we're gonna have 3 coordinates, x, or let's say this is x here, this is y, and here is z, right? So x is the interval AB. So this is A, this is B. Y is in the interval CD, and the height Z is in the interval RS. So this is RS. Okay. So AB cross CD would be just a rectangle, but then when you cross with the interval RS, you're gonna have a box. So you're gonna have like something like, let's see. Hopefully my graph is not too bad. So you're gonna have something like this here. right, so this is here and here. Okay, so you're gonna have a box. Um, so so what we are saying, guys, is that I mean, if you pick any point here inside this box, so if you pick I don't know, let's you pick a point P here, then this point, the x coordinate would be between A and B, y between C and D, and z between R and S, right? Anyway, so what we're gonna do now, guys? So this is should be from A to B. This should be from C to D, and the height here should be from R to S. Okay. So what would be the volume of this box? Well, of course, you're gonna just multiply the sides here, the length of the side, so the volume of the box, the volume of capital B, that would be, of course, the length of the first side, which is B minus A, times a D minus C, and times the height. The height would be the difference between R and S, so that's S minus R. Right, that's the volume of our box. Anyway, so what we're gonna do, guys, we're gonna integrate over this box, right? So now the goal is, so as we did for rectangles, so we're gonna so the goal would be to integrate over the box B. Anyway, so what we're gonna do, we're gonna divide the box B into sub boxes. So we divide. So you see, guys, when you integrate the function of single variable, so you have just one interval, right? So you're gonna divide your interval into sub intervals. When you have function of two variables and you want to integrate your function of two variables, so let's say you have a rectangle, so then you're gonna divide your rectangle into like small rectangles, right? Or sub rectangles, or wherever. Now we have a box, so we're gonna divide this box B into sub boxes, right? Boxes. So what do I mean by sub boxes? Well, you know, so you just gonna divide here. Well, it's not really nice graph, but anyway. So you're gonna divide this box into sub boxes, you know, so you're gonna get like a very small boxes, right? So this is what I mean by sub box here. Okay, somewhere here, right? So I'm gonna call these sub boxes, let's say B subscript. So B subscript. So you see, we have three different intervals, right? So we have to divide the three intervals into sub intervals. So when you divide the interval AB into sub intervals, so we're gonna have X, let's say subscript I minus 1, X subscript I, and then you're gonna divide the interval CD into sub intervals. So you're gonna have Y index J, Y subscript J minus 1. Do the same for the interval RS. So then you're gonna have in sub intervals, you know, Z subscript K minus 1, Z subscript K. Right. So I'm gonna call this box a sub box, the box B subscript I J K. Right. Now, my question for you guys, well, so what would be the volume of this sub box B subscript I J K? Well, so what I did, guys, so here we divided. So we divided the interval AB, CD, and RS into, let's say, n subintervals. Okay. So then the volume of the subbox B subscript IJK would be so then the volume of the subbox B subscript IJK is just let's say delta V. All right, that's actually delta X, delta Y, delta Z. All right, so what's this delta V? That's the volume element, right? This is my volume element. Okay, so what's delta X? Well, delta X, it's well, you divide the interval AB into n subintervals. So this delta X is just the width of the subinterval. So that will be B minus A, the length of the whole interval, over n, right? Because we divided the interval into n subintervals. Delta Y, same thing. It's D minus C over n. And then this delta Z is the same thing. It's just S minus R divided by n. Okay. So again, guys, I'm gonna just try to integrate this function of three variables over this box B. This is the function of three variables f, x, y, z. So what we're gonna do, we're gonna just consider a triple Riemann sum. Okay. So we're gonna have sum. So the I, the index I, you see, so here we have three indices, right? So we have I, we have J, and we have K, right? And because we divide each interval into n subintervals, so the index I would go from 1 to n, J from 1 to n, and K from 1 to n, right? So this triple Riemann sum would be, so the sum over I going from 1 to n, the same for J going from 1 to n, the same for K going from 1 to n, and then you're gonna have f of, let's say, xi, yj, zk times the volume element, delta V. Okay. Again, this delta V is just delta X times delta Y times delta Z. It's just B minus A over n times D minus C over n times S minus R over n. Anyway, so what will be the definition then of the triple integral? So it is like for a double integral or the single for a function of single variable. So it's going to be just the limit. So we define. So this is the definition of the triple integral. So define the triple integral of f of x, y, z over the box B. So we have this triple integral. So this is my function times the volume element. So that's dv over the box B. Okay, so this is my volume element. All right, and so by definition, this is just the limit n going to infinity. Of course, as n approaches infinity, all right, the sub boxes, they become smaller and smaller, right? So we're going to have a better approximation of our integral. So this is limit. Of course, we have a triple sum here. So I going from 1 to n, j going from 1 to n, and then k going from 1 to n of f of xi, yj, z index k times this delta v. Delta v, right? So that's the definition of this triple integral of the function f over the box b. So let me. Is there any question, guys? I mean, again, feel free to interrupt me and mute yourself. And if you have any questions, just let me know. All right. Well, let me make a couple of remarks here. So first, this dv or delta v is called a volume element because so if you integrate the function one. So a couple of remarks here. So the first remark is that this dv, so this dv is equal to, or the volume element dv is equal actually to dx dy dz. So this is the volume element because so if you integrate because so the volume of the box B, so that will be the triple integral of the function one with respect to this volume element, right, over B. Okay, so that will be the volume of the box B. And so how do we get the volume? So this is again the function one here. dv, we said it's dx dy dz, right? So x is between a and b. Y is between, we said y is between c and d, right? And z is between r and s. R and S. Okay. And actually, so if you integrate, you first integrate with respect to x, and then you integrate with respect to y, and then you integrate with respect to z, right? So if you integrate, then the final answer of this, that will be actually exactly the volume of the box B. So that will be this B minus A times D minus C times the S minus R. So that's exactly the volume of the box B. Okay, again, that's why we call this dV the volume element, because it allows you to actually compute the volume of this box. And actually, this is like a kind of a general statement. So you don't need to have a box. So if you have any solid S, then the volume of the solid S would be just the triple integral of the function of the constant function one, right? So this is, so in general, so if you have, let's say S is a solid in a three-dimensional space, right? So S is a solid in the three-dimensional space, in the space. So when I say the space, guys, of course, I mean the three-dimensional space, right? So then the volume of the solid S, that will be the triple integral of the constant function one with respect to the volume element dV over the solid S. Okay. I mean, this is just an extension of the result we had for in the two-dimensional case, right? In the two-dimensional case, if you have a region D in the XY plane, in the plane, if you have some region D in the plane, then the area of the region D would be just the double integral, right? So of the constant function one. So you can compare this. This is just an extension of um, extension of the two-dimensional case, right? So the area of a region D is just the double integral of the constant function one over the region D with respect to the area element, right? This is here, and this is the area element. All right, so where D, of course, here, where D is some region in the plane, right? Where D is a region in the plane, some region in the plane. So when I say the plane, of course, I mean a two-dimensional space, right? The plane. Okay, so that's the first remark. Of course, this is a three-dimensional. This is triple integral. This is three-dimensional case, but you can imagine. I mean, you can guess that we can extend these definitions actually to arbitrary dimension. Okay, so I mean, you can of course have you can extend these definitions to the four-dimensional space or the five-dimensional space or wherever dimension you have, right? So my next remark is that you can, I mean, we can extend all these definitions. We can extend all these definitions to any dimension, right? To arbitrary dimension. All right. What else? Another remark. Yeah, so that's one thing. Yeah, another remark is about the, remember guys, in the two-dimensional, I mean, for double integrals, we said we can switch, double integrals over rectangles. So we said we can switch, switch the order of integration using the Frobenius theorem. If you have some continuous function, you can always switch the order of integration, right? So then Frobenius theorem holds also in this three-dimensional case, right? So we can, so Frobenius theorem holds in this three-dimensional case. So we can switch. So if f of x, y, z is continuous, then we can switch the order of integration, right? So then we can switch the order of integration. Okay, and now let's have a first example of the a numerical example, order of integration. Okay, so let me show you. I mean, again, this is supposed to be kind of a review, but in any case, so I'm gonna just do a numerical example to show you how we evaluate the triple integral. So, how do we evaluate the triple integrals? Sorry, the triple integrals. So, for example, so let me just do an example here, numerical example. Example here. All right, so now we're gonna have triple integral. So we have three variables, x, y plus z squared. So that's my function f. We have dx, let's say dy, and dz, right? So let's say x is between 0 and 2. Let's say y between 0 and 1, and z between 0 and 3. All right. So this means, so here we have to, so first we have this x, right? So first we have to integrate with respect to x. So here we integrate. So of course you go from inside to outside, right? So first you integrate with respect to x, of course assuming y and z to be constant. All right, and then you integrate, with respect to y. So once you integrate with respect to x, then you're gonna get rid of the x, right? So you're gonna you are left with a function of y and z. Okay, so then you integrate with respect to y, assuming z to be constant. Once you integrate with respect to y, then you get rid of the y, and everything becomes in terms of z, right? So then last thing to do, of course, would be to integrate with respect to z. And then, so then last thing would be to integrate. Integrate with respect to z. Right? Anyway, so let me probably do the computations for this one here. Well, it's a triple integral, so it's going to be a long integral. But anyway, let's do it at least one time. Like in this example, so first you integrate with respect to x. So then, this y here and this v square both are constant, right? So x times y, y is a constant, so that will be x squared over 2 times the constant. Plus an integral of the constant z squared with respect to x, so that will be x times the constant the z squared. This is evaluated between 0 and 2, and then we keep the integrals with respect to y here and with respect to z, with respect to y. So here's a 0, 1, and then with respect to z, this is 0, 3. All right, so then you substitute x with 2 and 0. Substitute x with 2, that will be, so this is 0, 3, 0, 1. So that will be 2 squared over 2 times y plus 2z squared minus, and then x is 0. So it'd be just 0, right? Okay, let me write it down here. 0 squared plus 0 times z squared, and then dy dz, and this is of course 0. And then you're gonna have 0, 3, 0, 1. This is a 4 over 2, that's 2y plus 2z squared dy dz. Okay, so now we are left with a function of y and z. We integrate with respect to y now. All right, so this is with respect to y. Assuming z to be constant, so this is equal to, so here's my integral with respect to z. With respect to y, so 2y, integral of 2y would be y squared, integral of 2z squared constant, so it's just 2z squared y between 0 and 1. Substitute y by 1, that's 1 plus 2z squared, and then you substitute y by 0, you're gonna have just 0, okay? And then that will be dz. Okay, so now we are left with a function of z, of course. I'm sorry, this is kind of long, but I mean, we have to do it at least one time, right? So we integrate with respect to z, integral of 1, that will be z, integral of 2z squared, 2 is a constant, so I'm gonna just keep the constant. We don't worry about the constant. Integral of z squared is just z cubed over 3. This is evaluated between 0 and 3, right? So that will be 3 plus 2 times 3 cubed over 3, and then you substitute z with 0, it's gonna be just 0. So final answer, that will be so 9, right? 9 times 2, 18 plus 3, that would be 21. Okay, so if I'm not mistaken, the final answer would be 21. Right? Any question, guys, about this triple integral? All right. Anyway, this is not the hardest part, I guess. Okay, now I'm gonna apply Fubini's theorem. So I'm gonna probably give this as an exercise. So here's an exercise for you guys. So exercise. Okay, so please apply Fubini's theorem to so what do I mean here by applying Fubini's theorem is that I'm going to interchange by switching the order, switching the order of integration. Okay, so what I'm saying here, guys, I mean, we already computed this x squared xy plus z squared dx dy dz, right? And we got we got 21, right? X between, we said 0 and 2, y between 0 and 1, and z between 0 and 3. Right? So what we have to do, guys, is just try to switch the order of integration and see if you get the same answer. Of course, here, by switching the order of integration, there are different ways to switch the order of integration. So first case would be, or first case, oops, sorry. So case 1, so let's say, so we have the same function. And now let's say you integrate with respect to y, and then with respect to x, and then with respect to z. All right. Or you can also okay, so we have same function. You can also integrate with respect to y, but then z, and then x. Right. Or you can also well, there will be a lot of cases here. Probably you should try one of these cases, right? Just one of these cases. So case 3 is when you have xy plus z squared, then dx, but then you're going to switch the dy and dz. So that'll be dz dx, right? Now, there are 2 remaining cases. So let's say you integrate first with respect to z, right? You can integrate first with respect to z. So case 4, and then case number 5. So case 4 is when you integrate with respect to z first, and then xy, or z first, and then y, and then x. Okay. So what I'm asking you to do, guys, I mean, obviously that will be too long if you have to integrate to compute all these integrals, but just try to compute one of these cases, all right? Just one of these integrals, okay? So I'm gonna give you, let's say, 5 minutes, just to see if you get the same answer as I got in the example. Okay. So my question is, of course, is just to evaluate one of these integrals. Just one. Okay, let's say you have 5 minutes, guys, to evaluate one of these cases. So in total, guys, so when you switch the order of integration, so we have, in total, we have 6 different integrals, right? We have 6 different integrals because you can integrate first with respect to x, right? Like here, but then you can switch between y and z. Sorry, here it should be y here. Right, so you can integrate first with respect to x and then switch between y and z, right? Or you can integrate first with respect to y, like here, and then, you know, play with x and z. So you can play here with x and z, or you can decide to integrate first with respect to z, right? Like here, and then you can interchange x and y, right? So, I mean, in total, we have like 6 different um, triple integrals. But of course, there's all supposed to be equal using Fubini's theorem. So please just try to evaluate one of these integrals, not all of them, because we don't have time. That will be too long. Hopefully I got the right answer here. So you're supposed to get you're supposed to get 21, guys. If you don't get 21, it means either I'm wrong or you are wrong, of course. But I think um, my computations are correct. I think they're correct. So if we don't get 21, please let me know, because um, we can easily make mistakes, right? I mean, by the way, guys, I would assign, I guess, a new homework on homework number 2 on Thursday. It would be probably about the triple integrals. I guess today, I'm not sure if we're gonna finish triple integrals today. But anyway, probably gonna have we will finish triple integrals by Thursday. But then after that, after triple integrals, we're gonna do um, after triple integrals, we're gonna do the change of variables. We'll see. So if we finish triple, I don't think we're gonna finish triple integrals today. But so the next homework number 2, gonna be probably just about the triple integrals, right? And as I said, so after triple integrals, we're gonna have the change of variables, and then in change of variables, you'll see, guys. I mean, like. You can change the coordinates. So instead of using XY or XYZ, we can use polar coordinates or spherical coordinates or wherever. And sometimes that'll be very, very helpful. I mean, like in case you have like 1 minus x squared, integral of 1 minus x squared, that would be that will be very easy to compute if you use, for example, polar coordinates instead of the xy. If you use polar coordinates, that will be very easy to compute. So yeah. Anyway, well, first let's focus on this triple integrals. Let's finish the triple integrals, and then we'll see. All right. Anyone tried one of these cases? Did you get, guys, 21 as a final answer? I know it's kind of
I
long.
tried case 4 and got
Case
21.
You got 21, Alicia?
Yes.
Okay, cool. Means my answer is correct. Very cool. All right, very nice. Okay, so as I said, you have just to evaluate one of these integrals, guys, because it would be too much. So I'm gonna probably I should probably do one of these cases. Probably not. That'll be too much. Yeah, probably not. Yeah. So so Anisia, she confirmed my answer. So you should get 21, guys. Otherwise, probably you made a mistake somewhere. Anyway, so yeah. So by Fubini's theorem, the answer should be, your answer should be 21. And of course, when you change the order of integration, guys, you have to be careful here because, so for example, in the first case, you integrate first with respect to y. So then your y is between 0 and 1. So you should put 0 and 1 here, right? And then you have x. You have an integral with respect to x. X, we said it's between 0 and 2, so we should put 0 and 2 here. And then with respect to z, and then z is between 0 and 3, right? So we should put 0 and 3 here as bounds, right? etc. So just keep in mind your y is between 0 and 1, your x is between 0 and 2, and your z is between 0 and 3, right? Is there any question, guys, about these integrals? Any problem? Nope. Okay, cool. All right, so that's for triple integrals over boxes. Now, like as we did for regions in the plane, we started with the rectangles, and then we moved to elementary regions in the plane. So we're gonna do now elementary solids in the space. This is a little bit more complicated than the plane, right? So so now so now the goal would be to integrate. So we have this definition of triple integral over boxes. So the goal now, of course, is to extend this definition to triple integral over elementary solids in the space. So so now we're going to integrate over elementary solids in the space. Right? So what do I mean by this elementary solid in the space? Before the definition of elementary solid of the space, I need to explain, so remark here. So I need to explain the projection of a solid into a plane. So what's a projection of a solid into a plane? Okay, so let me well, I don't like the formal definition, so I'm gonna go first with an example. All right, so example. So again, I'm gonna need this projection of solid into plane to introduce the elementary solids in the space. So so I'm gonna explain first what do I mean by projection of solid into a plane. So I'm gonna go with an example. I'm gonna go with a kind of an easy example. I'm gonna go with a ball of radius 1 in the space. Radius 1 in the space. So that would be x squared plus y squared plus z squared. Less or equal to 1. So less or equal to 1. Okay. So when you say, of course, x squared plus y squared plus z squared equal to 1, that would be the sphere. So when I say the ball, that's the solid, that's the interior of the sphere, right? The sphere is just the boundary, right? It's like saying it's like the difference between a circle and a disc, right? The disc is the interior of the circle, right? So our solid here is this ball of radius 1. So S. So this is our solid here. S is this ball of radius 1. Okay, and so let me just probably sketch here this ball of radius 1. So we're gonna have 3 coordinates: x, y, z. We're gonna need, I guess. So we're gonna need, I guess, 1 here, 1. And 1, and we're gonna need, of course, -1, -1, -1, -1. But anyway, so the sphere of radius 1 would be this one here. All right, so right, so we have this ball of radius 1, right? That's my solid S. That's my solid S, right? And for example, what would be, the projection of this ball into the, let's say, the XY plane, right? So first question is, what's the projection of the ball into the XY plane? Okay, so when I say XY plane, guys, it means the plane of the equation z equals to 0, right? That's where z is equal to 0, right? So the XY plane actually contains the x-axis and the y-axis, right? That's the definition of the XY plane. Anyway, so what's the projection of S into the XY plane? So the idea is the following, guys. Geometrically, if you want to find this projection of this solid S into the XY plane, so what you do is you take all the points in the points belonging to this solid S. So for example, if you take, let's say, I'm going to take this point here. This point lies on the sphere, but if you take another point somewhere here, inside the ball here, or you can take this point here somewhere inside the ball, right? So what you do, you want to find, right? You want to find the projection of S into the XY plane. So what you do is you take the line passing through the point and perpendicular to the XY plane. So for example, for this point here, I'm going to take this line, right? It passes through my point. So I'm looking for the projection of this point into the XY plane. So I take the line which passes through the point, my point, and which is perpendicular to the XY plane, right? So here, we're going to have a right angle, right? Somewhere here. We're going to have a right angle. So the intersection, with the of your line with the XY plane, that will be the projection of your point into the XY plane, right? So that will be, so this point here, that's the projection of my yellow point into the XY plane. Okay, so this is like the geometric definition of a projection. You take your point, you take the line which passes through the point and which is perpendicular to your plane. So then the intersection of your line with the plane, that will be the projection, right? Does it make sense to you guys how I got this projection, right? So for example, the next point, like this one here, you're gonna do the same thing. You're gonna take the line, which is, which passes through your point and which is orthogonal or perpendicular to your XY plane. So you're gonna have some right angle here, right? And so the intersection of your line with the XY plane, that will be the projection of your point into the XY plane, right? So does it make sense to you guys? What do I mean by geometrically? What do I mean by this projection into the XY plane? Right? Just take the perpendicular lines passing through the point, right? Now, if you take the set of all the projection points, so like here in this case, if you take the set of all the projection of your points, then you're gonna get in the XY plane, you're gonna get this circle. Okay. So this disk here, so the disk here is, that will be the projection of S. This is the projection of S into the XY plane. Okay. So we have to take the set of all your projections. So you take all the points, in S, right? And you project them into your XY plane, right? and then you take the set of all your projections. That's the projection of your solid into the XY plane, right? So in this case, when you project your solid S into the XY plane, you get the disk, right? You get this disk of radius 1. So so when you take a look to the XY plane, you're gonna get a disk, right? This disk here. Right? So that will be the projection of, this is the projection of S into the XY plane. XY plane. Right? Of course, here it's 1 here. This is 1, etc. So it's just a disk, a radius 1. Okay, so this is like the geometric interpretation of the projection. Now, if you want to use the computations, all you have to do is just take, I mean, numerically here, if you want to just do some computations, you can just take the equation of your ball or the sphere here, right? So we are interested in the projection into the XY plane, right? So all you have to do is just make z equal to 0, right? Because XY plane, that's where z is 0. So you can see here, guys, if you equal z to 0, you get x squared plus y squared equals to 1. That's your circle, right? Or radius 1. So you can get the projection of S into the XY plane. So if you make S equal to 0, sorry, Z equal to 0, right? That's the equation. That's the equation of the XY plane. XY plane. All right. So then, your ball, x squared plus y squared plus z squared less or equal to 1 becomes x squared plus y squared. So here 0 is supposed to be 0 less or equal to 1. And that's exactly the disk, the interior of a circle, right? Which is the interior, the interior of a circle of radius 1. Okay. Okay, so that's what I call, again, that's what I call projection of a solid, of my solid S here, which is the ball into the XY plane. Of course, you can pick a different plane. Instead of XY plane, you can try, I don't know, another plane, XZ plane, or it doesn't have to be like some coordinate equal to 0. It could be also a different plane, like X plus Y plus Z equals to 1, or some, different equation, right? But in general, that's how it works. So that's the definition of projection of your solid into your plane. You just take your points, the points belong to your solid, take the lines passing through the points, and which are perpendicular to your plane, and then the intersection, the intersection of your line with the plane, that will be the projection, right? Does this make sense to you guys? This projection, this idea of projection of a solid into a plane. Anyway, this is just one example, okay, so why I'm talking about this projection of solids into XY plane or wherever plane you have, that's because of the definition of elementary solids in the space. So, okay, so let me probably introduce elementary. So now I can define, so now we can define elementary solids in the space. Right? So remember, guys, for elementary regions, we had like two different types of elementary regions, right? The first type was when x between two constant and y between two functions, and the second type is when your y is between two constant and x is between two functions, right? Now for triple integrals, we're gonna have like three different types. But each type we're gonna have like two subtypes. Okay, I know it's long, but let me do it. Let me introduce the elementary regions now. I guess we won't have time to have examples. Um, anyway, we will see. Okay, so let me first introduce the elementary solids in the space. So type 1. So type 1 elementary. Okay, type 1 elementary solid in the space. So first type would be, well, we're gonna have like two cases. We can write like just using the following form. So S, the solid S, would be the set, is the set of the points X, Y, Z, such that, right? This bar here means such that your Z is between two functions of X and Y. So Z is between, let's say, X, Y, G of X, Y, and H of X, Y. And, okay, so your Z is between the graph of two functions of X and Y. And the projection of S into the XY plane is actually an elementary region of the plane, is elementary region. Region of the XY plane. So what does this mean? Well, it means we're going to have two subtypes. So either your S is, so set of X, Y, Z, Z is between two functions of X and Y. Right? And then let's say, so the projection of S into XY plane is an elementary region, which means your X, for example, your Y is, let's say your X is between two constant, A and B, and Y between two functions of X, let's say beta X and alpha X. Right? Or the second case, right? S is, so S would be the set X of the points X, Y, Z. Z again between two functions of X and Y. But then Y would be between two constants, let's say C and D. And then X is between the graph of two functions, two continuous functions over this interval CD. So X is between, let's say, beta Y and alpha Y. Okay. So you see here, X between A and B, Y between two functions of X. That's an elementary region, right? Here the same. Y between two constant and X between two functions of Y. That's an elementary region, right? So in this type 1 elementary solid, you are saying your Z is between two functions of X and Y, and then the projection of of S of the solid into the XY plane is actually an elementary region in the plane, right? So this is type 1. Well, you can guess, like for type 2, you would have like, let's say Y between two functions of X and Z, and then the projection of S into the XZ plane is an elementary region, right, of the XZ plane. And then the type 3. So let me just write down here, finish this. So this is type 1. So type 2 would be, so S is a set of points, X, Y, Z. Now let's say Y is between two functions of X and Z. So G of X, Z, H of X, Z, right? And then the projection of X and projection of S into the XZ plane is an elementary region. An elementary region of the XZ plane. Which means that either X between two constant and Z between two functions of X, or Z between two constant and X between two functions of Z, right? The type 3 would be, so S, you're gonna have X, Y, Z. Now X, let's say, is gonna be between two functions of Y and Z. So G of Y, Z, and H of Y, Z. And then the projection of S into the YZ plane is an elementary region. Of the YZ plane, which means that Z is between two constant and Y between two functions of Z, or your Y is between two constant and Z between two functions of Y, right? So this is like the definition of elementary solid in the plane. In the last 3 minutes, I'm probably gonna have time to do just one example. Okay, so I'm gonna do more examples next time, guys. And of course, I'm gonna show you how to extend the triple integral over boxes to triple integrals over these elementary solids, right? And we'll have plenty of examples. The three-dimensional case, I mean, the triple integrals, sometimes they are kind of complicated. They're not always easy, but next time I'm gonna have plenty of examples, all right? So let me just finish in the last 3 minutes. I'm gonna do just one example to show you, well, an easy example, and then we're gonna have more, let's say, sophisticated examples next time, okay? So example 1, we're gonna have more examples next time. Well, let me just come back to this, the example of the ball. So S is, the ball, that's X squared plus Y squared plus. So this is the ball, which is bounded by the sphere. Let me write it like in this way. So the ball bounded by the sphere X squared plus Y squared plus Z squared equals to 1, right? Yeah, so this is Y, this is X, this is Z. So we have this ball here, right? That's my solid S. Anyway, so if you want to describe this this ball as a type 1, as an elementary solid of type 1, so type 1, if you want to describe it as type 1, then your Z should be between two functions, right? So type 1, we said, where is it? Yeah, here. So type 1, we said Z should be between two functions of X and Y, right? So here in this case, you can see your Z, your Z, the height Z is between the graph of these two functions here. So in the top, you have this here, right? And in the bottom, you have this here, right? So your Z would be between, you have x squared plus y squared plus z squared equals to 1. So if you solve for Z, then Z would be, of course, plus or minus, right? Because of the even power. So it's plus or minus square root of 1 minus x squared minus y squared, right? The top, here, this would be plus because high Z here would be positive. So this is plus square root of 1 minus x squared minus y squared. And the bottom here, that would be minus. So Z is minus square root of 1 minus x squared minus z squared, minus y squared, sorry. Minus y squared, right? Because in the bottom, below the xy plane, the height Z would be negative, right? So anyway, so your Z would be between these two functions. So your Z is between this minus square root of 1 minus x squared minus y squared and plus square root of 1 minus x squared minus y squared. Okay, so this would be like your g of xy, and this would be like your h of xy, right? So my Z is between these two functions, and then so type 1, we said Z between two functions, and then we said the projection of S into the xy plane, so it should be elementary region of the xy plane, right? So what's the projection of the ball into the xy plane? So I just explained in the previous example, the projection of a ball into the xy plane. So in this case, so then now the projection, it's just the disk, right? So projection of S into xy plane is bounded by the circle of radius 1, right? As I said, geometrically, it means just you're taking lines passing through the points in the solid and perpendicular to the xy plane. So then you take the intersection of the lines with the xy plane, or you can just set Z equal to 0 in this equation here, right? And you get x squared plus y squared equals to 1, right? So anyway, the point is a circle, we know that the circle is an elementary region, right? So this is my disk here. And so this is 1, of course, this is 1. So there are two different ways to describe this elementary region, two types. It's actually of both types. You can say x is between, -1, +1, and y would be between minus square root of 1 minus x squared and positive square root of 1 minus x squared. Or you can say, of course, y is between -1 and +1, and x is between minus square root of 1 minus y squared and plus square root of 1 minus y squared, right? Yeah, so anyway, you have the choice here. This disk is just of both type, right? Anyway, guys, I'm sorry I went over time. I know it's sometimes it's just too much, but yeah, I'm gonna stop here. I'm gonna continue on Thursday, and Thursday we'll have more examples of this elementary solids, right? And then I will show you how to integrate over elementary solids in the space. All right. Again, guys, if you have any question about the homework, you can email me anytime. And of course, it's due on Thursday. And I'll sign homework number 2 also this Thursday. All right, so I'm gonna stop here, guys. I'm sorry. I will see you on Thursday. Thank you, everyone.
Thank you, Professor.
Thank you, guys.